Hey guys, so number one, you'll notice that the screen is no longer shaking. That's because my stand finally came in, so you don't have to handle the like trippy sort of seizure-esque inability of me to be able to hold my phone still. So sorry about that before, but at least it's a little better now. So let's take a look at our first question. So it says a mixture of hydrogen and nitrogen in a reaction vessel is allowed to obtain equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of hydrogen, 2.46 atmospheres of nitrogen, and 0.166 atmospheres of ammonia. Now, think about that unit in atmosphere. An atmosphere is referring to pressure, right? Take a look at the equation. The equation is gases. So that kind of makes sense, right? And it says from these data, collect the equilibrium constant Kp for this reaction. So Kp does relate to pressures, and they gave you pressures, so you don't have to worry about any extra step here. There's no trying to relate Kc to Kp. That's not what we're doing here. What we're doing is we are literally, those are equilibrium pressures. We're going to write our equilibrium constant expression, and then we're going to plug those pressures into it, and we're going to solve for the unitless value that is Kp. All right, so now I'm going to rotate the phone down, and we're going to get to our piece of paper here. Okay, so first things first, we need to write our Kp expression. So Kp is equal to the pressure of ammonia, not squared, sorry, I wrote that 2 in the wrong place, divided by the pressure of nitrogen, also divided by the pressure of hydrogen cubed, right? That is what we know just from the question. Okay, now what we need to do is we need to plug in the values that they gave us. So, pressure of ammonia is 0.166 atmospheres, and that is squared, divided by the pressure of nitrogen is 2.46 atmospheres, divided by the pressure of hydrogen, which is 7.38 atmospheres, and that is cubed. Now, if you look at those units, they are not technically going to all cancel out with one another, right? They're not going to technically cancel out with one another because of the stoichiometry involved here, right? But remember, I told you that K is a unitless value. So don't worry about these, right? You don't even have to write them. If it's going to confuse you to write them, don't write them. Okay? All right. So now all you need to do is put this into your calculator. So we have 0.166 squared divided by 2.46 divided by 7.38 cubed. The biggest mistake people make here is they put this in their calculator wrong. So let me show you 2 different ways that you could do this and still get the right answer, okay? So you could put this in as 0.166 squared divided by, and then put all of this in parentheses, 2.46 times 7.38 cubed. That will work. Okay, what's another thing that'll work? Well, you could say 0.166 squared divided by 2.46 divided by 7.38 cubed. That would also work, right? So that's good, and that's good. But if you do this, if you put this in as 1.66 squared divided by 2.46 times 7.38 cubed, that is not okay. This will not work. Okay? But assuming you used one of the first 2 methods I showed you, you should get the correct answer of 2.79 times 10 to the negative 5th. Okay? 2.79 times 10 to the negative 5th. All right, so let's look at another example, okay? All right, what about this one? So here, same equation, Haber process again, the production of ammonia from nitrogen and hydrogen. All right, but in this case, they gave us Kp. All right, so they gave us Kp, and they're telling us that, again, we have an equilibrium mixture. Notice the temperature has changed, but what else changed? Let's go back a question. So the temperature changed, and the value of K changed, which should be correct, right? Because K is temperature dependent. So we're looking at a new temperature and a new K, and they give us the partial pressures of hydrogen and nitrogen. So they tell us that hydrogen is 0.928 atmospheres, and they tell us that nitrogen is 0.432 atmospheres. They're looking for the pressure of ammonia. So this is kind of exactly like what we did before. It's just that now your X, what you're solving for, is no longer K. Now it's one of the concentrations. But we're going to start it the exact same way that we started the last one, okay? So let's go down to our sheet of paper. All right. Let me tighten this up. Woo! Sorry. Righty tighty. All right. Cool. So now let's look at this. So let's write the same Kp expression again. So Kp is equal to the pressure, the partial pressure of ammonia squared, divided by the partial pressure of nitrogen, divided by the partial pressure of hydrogen, cubed. Now, we know what this is equal to. We know that this is equal to 1.45 times 10 to the negative fifth. All right? We know the value for nitrogen. Nitrogen is 0.432. We know the value for hydrogen. Hydrogen is 0.928 cubed. What we don't know is we don't know the pressure of ammonia. So we don't know the pressure of ammonia. But don't forget that that is X squared, right? Because the square there, that's X squared. So at this point, you've just got some algebra in front of you, right? So you need to take, so what I would do is I would cross multiply, right? So this would become X squared is equal to 1.45 times 10 to the negative fifth times 0.432 times 0.928 cubed, right? So then an X squared is going to be equal to, let's put that in our calculator, 1.45 e to the negative fifth times 0.432 times 0.928 cubed. And I get 5.01 actually, 5.01 times 10 to the negative sixth. Now, this is not K, which means this is eventually going to have a unit. We'll add the unit in a second. But this is X squared, so now we need to take the square root of both. So if I take the square root of that number, I get that X is equal to 2.24 times 10 to the negative 3. And remember what X is equal to. X is equal to the pressure of ammonia, which should have a unit. So that is atmospheres. Okay? And if we go back to the slide, we got the right answer. All right? So that's the end of this video. We'll pick back up with screencasting in video 3.